numbers for us to write, especially the numbers, I think. But the observant viewer will notice that we haven't quite covered all the bases with this multiplication rule that we've given. Because what happens when we multiply, say, the empty m set with a natural number? This is also a natural number, so we'll call 0. What happens if we take 0 times, say, this m set? Okay, so the rule is, well, we're supposed to consider all possible products of the form unit times unit, where one of them is obtained or taken from the first m set and the other one's obtained from the second m set. Okay, but in this case, there are no units in this first thing, so there are no such products. We cannot form any products, unit times unit, where they vary respectively from both of the ingredients m sets. We cannot. And so the product of these two natural numbers will also be necessarily empty. Another thing to observe is that associativity of multiplication, which is a more subtle issue, right? Why is 3 times 4 times 5 same as 3 times 4 times 5? That essentially really ultimately boils down to this associative law. The fact that units times units times units is the same as unit times unit times unit. That's true because this in here is a unit. So this is just unit times unit. So this left-hand side is just what we call unit. And it's also true of the right-hand side. That's a unit and unit times unit is unit. So we're getting units on both sides. So very cool. So this fundamental associativity at the level of the units themselves then goes up to associativity of multiplication of natural numbers. So if we want to multiply, say, what we would call 2 times 4 times 3, in this order, we get the same as 2 times 4 times 3, because all of the various products, say, that are involved on the left-hand side look like what? So the entries of this thing here are things in the form a unit here times a unit here. Okay. And then when we multiply by this set, we're taking a unit here times a unit here, multiplying that combination with one of the units over here. Okay. But on this side, what we're doing, correspondingly, is those same units that we flagged, maybe we color them red or something temporarily. Over here, we would see them again, but then they would correspond to a product over here. So here, the red one times the red one would appear on the right-hand side, and multiplied by the red one here. So basically, we're using the same law here, just applying it to all these possible triples of units obtained, unit here times unit here times unit here. So we've seen this kind of argument before in the maximal kind of situation. We observed that if we have a associative product at the pixel level, that then lifts to an associative product at the maximal level. Once we just define maximal multiplication as the m set extension of pixel multiplication. It's exactly the same kind of story, same kind of pattern. So really, this is the single associativity at the level of these units, which is really responsible for the associativity of natural number multiplication. So there's arguments to be made here, and you could convince some primary school students, I think, by going through this carefully with some examples. But it would be just orders of magnitude more complicated to try to convince someone of the associativity of multiplication using the 20th century set theoretical formulation. Okay, that's just orders of magnitude much more complicated and convoluted. So we are really cutting to the chase here. I think we're really boiling things down to pretty well the simplest thing that they possibly could be with this m set point of view. I think it's valuable to say a little bit more about the role of nothing in this story so far. So we've used nothing to create this empty m set, which is then going to play the role of 0. That's sort of in the traditional way, very much like in the standard formulation of things. But in addition, I think it's important to recognize that there's now also a new role for nothing, which is not just contained in the empty set. So our basic multiplication, for example, we stated it in terms of just being between units and unit times unit equals unit. But we saw that actually it's a little bit more expansive, a little bit more precise to also say what happens to the nothing times unit. So there's really these two aspects of things. There's the nothing and the something. And what we've already observed or defined is that something times something equals something. The story is really completed by this more elaborate multiplication table, which includes also the fact that nothing times nothing equals nothing. So you can see that there's nothing and nothing times nothing equals nothing. And also that nothing times something, represented by that entry there, is the same as something times nothing, represented by that entry there, which is nothing. Okay. So the true multiplication table, sort of at the level below the natural numbers themselves, arguably has these two objects or two concepts involved. There's both the nothing and the something. It's just that the nothing, we're agreeing we're going to write it as an empty page, or as an empty piece of our page, and so it ends up looking blank. Okay, but it's a new kind of way of thinking about nothing and the role of nothingness, and we're going to actually have something blank. It's not going to be a symbol that represents that blankness. The actual blankness itself is going to be addressed. We're going to acknowledge it, to let it be what it wants to be. It's just empty. And we look and we see, there's emptiness there. It's not just something that's forgotten to write something. Okay, it's meant to be empty. It is empty. It's a new kind of thinking that's going to be very valuable for us. It's very oriented towards an M-set point of view. When we're doing arithmetic with M-sets, and we're going to jack this up to algebra involving M-sets as well, linear algebra as well, we're going to see more and more the usefulness of being able to think about nothing as just being an empty part of the page. Nothing represented by a symbol, just letting it be nothing. Okay, Okay, so we have the beginnings now of a new kind of arithmetic, right? An arithmetic which is multi-step oriented, which incorporates these fundamental aspects of nothing and something, and which really has something aligned very much with sort of naive layperson's approach to what natural numbers might be, at the most sort of simplistic kind of level. So I think there's going to be a lot of theoretical implications of this, but there's also educational aspects that I think are worth touching upon. In particular, there's the connection between these numbers that we're invoking here and the names for the numbers. So we need to have a discussion about the importance of naming numbers, which also touches basically the issue of ordering numbers. So those two issues are closely related, ordering and naming. And they're both things that impact very directly on young people's original understanding of arithmetic, how they think about what arithmetic and natural numbers is. So I'll go join for that. I'm Noah Robert. Thanks for listening. Good day, I'm Noah Robert. Today we want to have a look at the role of the term nothing, the concept of nothing in mathematics, which historically has been very interesting. It's a sort of nebulous concept, of course, that a lot of people have different points of view towards. And what I'd like to do is I'd like to introduce a really dramatically new way, an additional new way of thinking about nothing and its role in mathematics. So in preparation for our discussion of that, let's have a look at some of the history. So a good place to go back to is the ancient Babylonians. Babylonians were sort of the geniuses of the ancient world long before the Greeks came on the scene. They had a very highly developed, original and powerful mathematics. So around 3000 BC, their culture developed in the Mesopotamian area, Tigris, Euphrates rivers. And they had a sexagesimal system, which means base 60, very interesting. And they also used a floating point positional system, very much like the one we do. So they used basically only two symbols, so a symbol for 1 and a symbol for 10, which they wrote with this sort of wedge-like implement that they used to write on clay tablets. So to express 47, they would make 4 of these 10s and 7 of these 1s, and you could arrange them in something like this, and that would be 47. So they used these to represent the numbers from 1 to 59. They are the corresponding digits for the Babylonians, just as the numbers 1 to 9 are for us. Well, actually, we use 0 as well. So then otherwise what they did is they had a base 60 representation so that they would club their numbers in various places, really. So this representation here, there'd be a 47 visible there, and here you see a 21, here there's some kind of space, and before we did is a 2. So this would represent for them, well, 47, 21 times 60, so this would be the 60th column, and 0 60 squareds, and 2 60 cubes. So altogether 2 times 60 cubed plus 21 times 60, we'll ignore this one, plus 47 for a total of what we would call 217,307. Now, an interesting aspect of their arithmetic was that they didn't really have a very clear or concrete representation of the decimal point. So there was some kind of ambiguity in their system. On another occasion, they could have represented this as being 21 ones, 0 60s, 2 60 squares, and 47 over 60. This gave them a flexibility that was actually quite useful. So what's interesting for us is their use of the space to represent zeros. They have a very clear idea that it works powers of 60, and if we're missing the power of 60, we'll just leave a space. We're not going to put anything there. The reader should be able to see the space here and sort of register that we're missing the 60 squares. So we have 60s and 60 cubes. So this is going back quite a long time, and so this really is a use of the decimal kind of system, very much like the Indo-Arabic one that we use, with the notable exception that they're working in base 60, and that they don't have an explicit form for a placeholder, but they're using the space pretty well exactly in a corresponding way. So they can certainly deal with numbers pretty well the same way that we can. Now, the Babylonian culture lasted a long time, talking about several thousand years span. And in the later part of this time frame, around 300 BC, there was a great flowering of astronomy and work in that direction. And part of that story was a very interesting development, that the Babylonians started to use actually an explicit symbol to represent this placeholder that previously they just had a space for. So this is actually the first recorded use of a symbol for a 0, which predates the Hindu development, actually. So here's what they did. They employed basically a similar kind of symbol to their number 2, just these two sort of wedges coming down. But they're now at an angle, and they're kind of a little bit above the regular reading of things. So they can see that as we're reading this here, this symbol here represents not a explicit number 2, but rather it's a placeholder for the 0. So they can read this as 2 times 60 squared plus 0 times 60 plus 24. Here we are, 7,224. Now, this symbol here really is only being used as a placeholder. Okay? It's to make more explicit, more unambiguous the fact that there is nothing in this place particularly, right here. It's not the case that this symbol was used as a separate number. So that was the development that the Hindus get credit for. Okay? So they did not have this idea that there's a new number, which is these two slanted symbols. Nevertheless, it's really the first use of the term zero, and the astronomers actually did employ this notation. However, it was never really equated with nothingness. We didn't have this idea that there's nothing, and that nothing is actually represented by this particular symbol explicitly. Now, many histories of mathematics concentrate on the Mediterranean area and the Asian developments as well. Of course, there was also very important cultures in the Americas, Mayans, Aztecs, Incas. And the Mayan culture is particularly interesting because they have a very interesting arithmetic and quite sophisticated calendar reckoning and corresponding astronomy. So in Central America, the Mayan culture, well, it was been around from at least 2000 BC, but there was a classic period from 250 AD to 900 AD that things really developed in a rather sophisticated way. And we know that they had a so-called digesimal system, which is base 20. And it was actually relatively efficiently written down with only 3 symbols, more or less. A symbol for 0, which was this sort of odd, kind of eye-shaped thing, and in fact there were quite a lot of variants on the way of writing that 0. And then there was a dot, which represented 1, and a horizontal bar, which represented 5. So they would count 0, 1, 2, 3, 4, 5 like this, 6 like this, up to 19. And then after 19, well, then they had a base 20 system, so these were sort of the basic digits that they would use, and then they would have these things stacked up in a vertical system, not a horizontal one. And they were very interested in astronomy and calendars, and that explains a little bit that the system for stacking things up was not quite what you would expect in a base 20 system. There was an important twist involved. So here, for example, is a Mayan number. So we see these symbols stacked one on top of each other. We recognize this one here is the symbol for 11. It has 2 5s and a 1. And then there's a 0, and then there's a 2, and then there's a 3. So what do these various things represent? Well, the bottom one was 11, or 11 ones. And here we have 0 20s. But the next level does not correspond, as we might imagine, to 20 squares. This next level actually represents how many 360s we have. So this would mean that there were 2 times 360. And the next level represented 20 times 360. So after this, we keep multiplying by 20, but we have this basic 360. So this means that we have 320 times 360s. So I think that's a total of 22,361. So there's certainly an unevenness to these levels. We have 1s, and then 20s, and then 360s, and then 20 times 360s, and 20 squared times 360s, and so on. And the reason for that is because they were very interested in the calendar. They had a very good understanding of astronomy and the year especially. So they knew there were 365 days a year, and so 360 was kind of the closest to that. So they had a splitting up of 360 into 18 periods of 20. So it's 18 times 20, and then there were 5 left over. And it was because of that 360 that appeared in their calendar that they had a number of systems that kind of reflected that aspect of things. So their numbering, or the numerology, I think was very closely connected somehow with the year and days and time. So it was an idea of their accuracy. They knew that the solar year actually was a little bit more than 365 days, and effectively they knew that in our language that there were 365.242 days in a year, while our current understanding is that's 365.242198. So this is pretty impressive kind of accuracy in their understanding. So the Mayans did have a symbol for 0, and they used that in their positional representation of numbers, not so much different from the Babylonians. Now, what about the ancient Greeks, who were, of course, sort of the powerhouse of ancient mathematics in terms of developing the geometry and mathematics that we know today? Well, their arithmetic was not as impressive as their geometry. They certainly knew a lot of interesting things about arithmetic, but their actual notational arithmetical tools that they had were not always very powerful. In fact, often they would use the Babylonian system to make calculations. They had a kind of an alphabet kind of system where they represented numbers by letters of the alphabet. But this was cumbersome, and they did find that the Babylonian system was useful to borrow. But we can also see that they philosophically were not inclined to think about 0 as a very important concept. Philosophically, they did not like, or they were distrustful of this idea of the void or nothing. And maybe we can attribute that a little bit to their emphasis on geometry. So, for example, if you had a very geometrical approach to numbers, which they did, they like to think about numbers as being represented by physical or geometrical patterns or designs. So, for example, triangular numbers figured prominently in their thinking, 1, 3, 6, 10, and so on. And if you're thinking about something like triangular numbers represented in this very physical way, with these little triangular piles of circles, then it's not very natural for you to want to consider 0. 0 doesn't really figure in this, because it's clear that this pattern of triangular numbers really ought to start with 1. That's the starting point. That's the next one. That's the next one. It's somehow unnatural to talk about 0 in this context. So Aside from their geometrical inclination, they also had very strong ideas about philosophy. They thought very deeply about what the world was really about. And they came to this conclusion that it was not really proper to try to make something out of nothing. So, the idea of nothing or a void was not sufficiently rich to be able to convert that into something. In some sense, that's what we're doing, right? When we're thinking about zero, we're thinking about nothing, and then we're writing a symbol to represent that nothing, and then that symbol becomes something that we manipulate along with other numbers. So, in some way, we're creating something out of nothing. Not the use of a modern symbol like this. But the Greeks did not like that way of thinking. They thought of both of the infinity and the void as things to be avoided, conceptually. They were problematic. So this philosophical orientation was well expressed by a prominent Greek philosopher, Parmenides, who was a big influence on Plato. And he wrote on this topic in a number of different places. So here's some quotes from Parmenides. He said that it is necessary to speak and to think about what is. For being is, but nothing is not. Okay, this is in the direction of we should talk about things which actually are. We can't talk about things which are not because they're not. Another quote, nothing comes from nothing. This is the idea that you can't take nothing, that concept nothing, and create something out of it as a vacuous kind of activity. You shouldn't do that. So we also read with him that for this view that which is not exists can never predominate. He's saying that the idea that we can consider that which is not, so that which is not, actually objectify that and create something out of it, that's not a valid way of thinking. So Parmenides had a big influence on Plato, who actually named one of his dialogues after him. And this really, was representative of the Greek way of thinking. It explains to some extent why theirs was not a fertile arithmetic for this idea of a symbol for zero to develop and blossom. I'd like to mention also that the Hebrew tradition is also in this direction. So in the Hebrew tradition, the void is also treated with suspicion, and one tries to avoid it. So the void is considered to be a state of separation from God. So first there was a void, then there was God creating other stuff, and so the void is some kind of thing that we want to stay away from. It's not pleasant. So there's philosophical orientations that are very close to people's thinking about this subject. What does it mean to contemplate nothing? For example, what would the world be like if there was nothing? It's a very profound question. And people have been thinking about these kinds of things for a long time. And one's orientation towards this kind of philosophical position would naturally influence one's mathematics and the kind of mathematics that one might want to do. And so now we come to the heroes of the story. The culture that really introduced zero the way we know it now. And now we recognize that this was a fundamentally, crucially important development in history of science. And I have talked about that in a previous video on the Hindu-Arabic numbers. So we're talking about ancient Indian philosophy, religion, mathematics. The Indus Valley culture goes back to around 3000 BC. But we have evidence to suggest that they were thinking along somewhat modern lines around 350 BC, where the Brahmi notation for numerals was starting to look pretty similar to the modern system. And they had a positional base 10 system that was in place around 500 AD. So here are some original kind of numerals. You can sort of see some similarities with some of our current numbers. Now, what's interesting in the Indian point of view here is, amongst other things, is that their philosophical orientation seems to predispose them towards being happy with the idea of thinking about nothing as a legitimate object for study and incorporating into mathematics. The Indians were not afraid of nothing philosophically. In fact, they had a kind of reverence for it. They were very comfortable with the idea of nothingness and emptiness. Simplistically, we could say that nothing was viewed as a state from which we arise, and it's a state that we eventually return to. So, from an Indian point of view, there's nothing to be afraid of there. It's a sort of natural part of the whole story. In any case, in Sanskrit, they had lots of different words representing different aspects of emptiness, void, nothing, and so on. So they conceptually had a framework in which nothing naturally played a reasonable role. And this was then, of course, very crucial in this development after they had these numbers to eventually introduce actually a symbol for zero. That turned out to be another number, essentially on par with the ones that they already have. So we have evidence that dot for zero was in place around 200 BC. And that gradually was then replaced with the most familiar round circle zero. And by around 500 AD, it was in place as a placeholder in a decimal system, pretty well the same as we have today. And then we come to Brahmagupta, prominent Indian mathematician and astronomer, who around 620 AD took an important additional step to establish zero not just as a placeholder in a notational system for more general numbers, but actually to recognize that zero was an entity that had some independence, had a role to play, and that role in fact turned out to be a rather important one in arithmetic. So that zero could be the result of an arithmetical computation. So 5 minus 5 equals 0. That is an equation that you could actually write down, whereas formerly it was difficult to say that. 3 plus 0 equals 3. You can multiply by 0. 0 times 7 equals 0. You can subtract 0 from something.